Section 3.11 Generalized Compressibility Chart. So far we have used thermodynamic property tables for accurate thermodynamic property data, but it is not always available. We are going to introduce a simple but very powerful equations of state to describe the gas behavior. It is called the ideal gas law. It is expressed PV equals RT, or it can be written on a molar basis. PV bar equals R bar T. So P is pressure, V specific volumes, R is called gas constant, T is temperature. So pressure and temperatures are absolute values. The gas constant R is different for each gas, and it is determined from the universal gas constant divided by the molecular weight or molar mass, M. The ideal gas law provides the pressure, specific volume, and temperature relations of an ideal gas. We are going to talk more about the ideal gas law in the following section. So in this section, we focus on the real gas. So real gas does not satisfy the ideal gas law. So we introduce a dimensionless correction factor to compensate for the deviation from the ideal gas. The compressibility factor is used to represent the deviation from ideal gas behavior. C is expressed PV bar over R bar T, or it can be expressed in mass base Z equals PV over RT. So it's similar to ideal gas law. For an ideal gas, Z is 1. For real gases, Z can be either less than 1 or greater than 1. The compressibility chart is used to determine the compressibility factor. The chart is based on the experimental data for 10 gases. In the legend, it shows 10 gases. The compressibility factor is plotted in function of reduced pressure, PR, and reduced temperature, TR. So compressibility factor, Z, function of reduced pressure, reduced temperature in this chart. Y-axis is going to be compressibility factor, Z, which is dimensionless. X-axis is going to be reduced pressure, which is also dimensionless. These solid lines indicate reduced temperature, that is also dimensionless. So in general, real gases behave differently at a given temperature and pressure. But if we use the normalized pressure and temperature relative to the critical temperature and pressure, we'll be able to see the general behavior of various gases. So PR is called the reduced pressure, defined as the pressure over the critical pressure. So critical pressure is the pressure at critical point. And the critical point is where the saturated liquid line meets saturated vapor line. TR is called the reduced temperature, defined as the temperature over the critical temperature. They are dimensionless or normalized with respect to the critical temperature and pressure. So gases may have different critical pressure and temperature, but the dimensionless chart shows that Z factor for all gases is approximately the same when the gases have the same reduced pressure and temperature. In the generalized compressibility chart, the solid line labeled with TR values represent best fit to experimental data. So this chart is based on the experimental data. Smaller variation in Z is observed as TR takes higher values. So TR here is 2, 1.5, 1.3, 1.2, 1.11. So as the TR increases, the variations of Z is smaller. Z is approximately 1 at high temperature. When the reduced temperature is 2 or higher than 2, actually the lines closer to 1, this horizontal line. And Z also approaches 1 at low pressure. X-axis represents reduced pressure. So as the pressure approaches 0 and Z value approaches 1. And Z value is smallest at the critical points, where the reduced pressure is about 1 and reduced temperature is about 1 at this point. All gases approximately have the same value of Z at the same reduced temperature and pressure. However, the chart should be used to estimate the PVT data, pressure, specific volume, temperature data, and use the chart if all that is known about the gas is the critical pressure and temperature. Let's see an example. We are going to determine the specific volume of water vapor at 20 megapascals and 520 degrees Celsius. And we are going to use the generalized compressibility chart to determine Z. And from Z, we are going to determine the specific volume of water at the given condition. So to use the compressibility chart, we need to determine reduced temperature and reduced pressure. See table A1. For water, reduced pressure and reduced temperatures are given. So we calculate reduced temperature and reduced pressure. And we are going to use the compressibility chart to determine Z. And figure A1 shows the compressibility chart. And you can see the range of the reduced pressure between 0 and 1. These charts can be found in the appendix in our textbook. From this chart, we can read the Z values more precisely. At reduced pressure 0.91 is about here, and reduced temperature 1.23. So this solid line indicates reduced temperature. And 1.2 is here, and 1.3 is here. So 1.23 is somewhere in between these two lines. And we need to find where the line for reduced temperature and pressure meets. So read the Z values at this point. And it's about 0.83. So Z is defined PV RT. So we need to determine specific volumes of water vapor. V is C RT over P. C is 0.83 and the gas constant of water vapor divided by the molecular weight times temperature 520 degrees Celsius, or make sure that you use the absolute values of temperature and pressure. So this is how we determine the specific volumes of water vapor without using the thermodynamic tables, but use the compressibility chart with the compressibility factor Z. Section 3.12, Introducing the Ideal Gas Model. So we are going to talk about the ideal gas law more in detail. Ideal gas equation is expressed as PV equals RT. The equation is very simple and it is convenient to use. So the ideal gas obeys the ideal gas relations. It is called the equation of state since the ideal gas law provides the pressure, temperature, and specific volume relations for a substance. P is the absolute pressure. Do not use the gauge pressure in the ideal gas equation. V is the specific volume, and R is called the gas constant. The gas constant is different for each gas. It can be calculated from the universal gas constant, R bar, divided by the molar mass or molecular weight of the gas. So the universal gas constant is used for any gases. It is divided by the molecular weight of the specific gas to determine the gas constant of the gas. So for example, we want to determine the gas constant of the air. Molecular weight for air is 28.97 kilogram per kilomole. So the gas constant of air is universal gas constant divided by the molecular weight of air, 8.314 kilojoule per kilomole, Kelvin, divided by 28.97. So this is the gas constant of air. So the gas constant depends on the molecular weight of the gas. The gas constant can be found in table 3.1 and the molecular weight of various substances can be found in table A1. T is the absolute temperature in Kelvin or degree Rankine. Degree Celsius or degree Fahrenheit need to be converted to absolute scale for use in ideal gas equation. Alternatively, the ideal gas law is expressed in different ways. Pressure times volume equals MRT, mass times R gas constant times temperature. PV bar. V bar is volume of the gas divided by the number of mole. R bar is the universal gas constant. PV equals N R bar T. They are all identical. Another characteristic of ideal gas is that the internal energy and enthalpy are only function of temperature. The state principle for a simple compressible system requires two independent, intensive properties to fix the state. To determine the internal energy or enthalpy, two independent, intensive properties were needed. But for an ideal gas, the internal energy and enthalpy are determined by the temperature only. That means, at a given temperature, the internal energy of an ideal gas can be determined. The enthalpy is defined as the sum of internal energy and PV. And PV equals RT for an ideal gas. For an ideal gas, U is a function of temperature and R is gas constant, T temperature. So we can say that the enthalpy is also a function of temperature only. When the system containing ideal gas undergoing a process with no mass change, the ideal gas can be written for mass. PV equals mRT, m equals PV over RT. At state 1, P1 V1 over RT1. Since mass doesn't change during the process, we can write P2 V2 over RT2. So R cancels out. P1 V1 over T1 equals P2 V2 over T2. Or we can take a different approach to explain this. For an ideal gas with constant temperature, PV mRT, we still consider mass is constant during the process. We also assume temperature remain constant during the process, so we can say PV is constant during the process. So P1 V1 equals P2 V2. And this is called Boyle's law. If the process undergoes a constant pressure process, M is constant, R is constant, and P is constant, so V over T is constant. So V1 over T1 equals V2 over T2. And this is called Charles' law. Combining these two laws, PV over T is constant. Real gases may be approximated as an ideal gas when the density of a gas is very low. That is when the temperature is high or the pressure is low. So at the very low pressure, the real gas is closely approximated as ideal gas at all temperatures. So how do we determine if the real gas can be approximated as an ideal gas? So evaluate the compressibility factor Z. So if it is close to 1, we may use the ideal gas model. In our textbook, the problem statements will clearly indicate whether we may use the ideal gas model. And we'll use the ideal gas equations for air, oxygen, nitrogen, carbon dioxide, carbon monoxide, and hydrogen. Example 3.8. 1 pound of air in a piston cylinder assembly undergoes a thermodynamic cycle consisting of 3 processes. Process 1 to 2. Constant specific volume. process 2 to 3, constant temperature expansion. Process 3 to 1, constant pressure compression. At state 1, temperature is 540 degree Rankine and the pressure is 1 atmospheric pressure, ATM. At state 2, the pressure is 2 ATM. Employing the ideal gas equation of state, so we consider air is an ideal gas. Sketch the cycle on PV coordinates. Determine the temperature at 2 in Rankine, degree Rankine. Finally, determine the specific volume at state 3 in cubic feet per pound. So first we need to know how the general shape of the PV diagram for ideal gas. Ideal gas satisfies PV RT. So if the temperature is constant, R is constant, and PV is constant. Y-axis pressure, x-axis specific volume. PV is constant, so P pressure is inversely proportional to V, so the shape will be like this. And this is at constant temperature. And if the temperature is higher, we will have another curve like this. In this direction, temperature increases. So this is the constant temperature lines on PV diagram for ideal gas. So assuming this is state 1, at state 1, temperature 540 degree Rankine. So this is constant temperature line. And the pressure is 1 atm. This is atm, 1 atm. So state 1 to state 2 undergoes a constant volume. So it moves straight up. So since this is specific volumes, remain constant during the process. And the pressure is 2 atm. From state 2 to state 3 undergoes a constant temperature expansion. So specific volume increases in increasing V directions. So the process moves to the right. And this line, and this is the constant temperature line. So it moves like this. And state 3 to 1 is a constant pressure compression. So the pressure at state 3 is also 1 atm. It's a compression process. Volume decreases. So direction of the process is in decreasing specific volume. And we are going to determine the temperature at state 2. And we are going to use ideal gas model. Pressure times specific volume over temperature is constant. So we can write P1 V1 over T1, P2 V2 over T2. Since the specific volume at state 1 and state 2 are equal, we can cancel out the specific volumes and solve it for T2. So next we need to determine the specific volume at state 3. So we are going to use the same ideal gas model between state 2 and state 3. So during the process 2 to 3, temperature remain constant. So we cancel out temperature and solve it for specific volume at state 3. and the pressure at state 3 equals pressure at state 1. And the specific volume at state 2 is also unknown. So instead of calculating the specific volume at state 2, PV equals RT. So we can rewrite it R T2 over P1. So gas constants for air. So we were able to determine the specific volumes and temperature using the ideal gas law.